In this section we talk about differential equations, and we've already talked a little bit about differential equations in this course and in Calc 1. And a differential equation is essentially an equation relating some unknown function and one or more of its derivatives. And here are some examples. Here's an example from earlier in the course where the rate of change of a function is proportional to the size of the function, and we use that to describe population growth in our section on exponential growth. A more realistic differential equation describing population growth is given on the right, and this takes into account some limiting factors in the population. We can describe the motion of a spring with a mass attached by a differential equation. On the one hand, the force acting on the spring is described by mass times acceleration, and x here is the distance of the end of the spring from the spring's natural length. And on the other hand, we have Hooke's law, which says that that's some constant times the actual value of the distance. And this gives us a differential equation describing the motion of the spring without damping, and this turns out to give us harmonic motion. In general, we'll look at examples like these of first-order differential equations, and we'll solve them in the next few lectures. And in all of these, the derivative dy dx or y prime has order 1. So the highest derivative here is a first derivative appearing in these equations. And the order of a differential equation in general is the order of the highest derivative that occurs in the equation. And so here we have 3 first-order differential equations. And of course the solution to these differential equations is some function y, which is a function of x. Here's an example of a second-order differential equation. This could be the equation describing the motion of a spring. And you see that the derivative here has order 2, and that's the highest order of any derivative in the equation, so this is a second-order differential equation. On the other hand, in this equation, even though v of t itself is squared, here this equation relates the function v and its derivatives, and v is a function of t. And so the order of the highest derivative in this equation is 1, and therefore the equation is a first-order differential equation. When we talk about a solution of a differential equation, if the equation relates a function y of x to its derivatives, then a solution is a function of the form y equals some function of x, so that when we plug it into the equation, it fits in the equation. So for example, if I were looking for a solution of y prime equals x minus y here on the right, I'm looking for a function where y is a function of x, which fits this equation. And in fact, you'll see that this function here on the bottom is the actual solution to the equation, because when I take the derivative of this function, y prime, I get 1 minus e to the minus x, or 1 minus 1 over e to the x, which is the same as x minus all of this. So when I plug in this function on the right and I plug in its derivative on the left, I get equality here, so it fits the equation. And you can check and figure out which of these on the right are solutions to these equations on the left by taking derivatives and trying to fit them into the equations. here we have a differential equation, and this is a type of differential equation that we've studied in Calculus 1. And the idea here is a solution to this equation is an antiderivative of this function. It's some function y, a function of x, so that the derivative of y with respect to x is e to the x over 1 plus e to the x. And you saw that the antiderivative, or the solution to this equation, was in fact a family of functions. And here we've drawn some members of that family. They're all related by a constant, hence we add the constant to the solution when we write down the solution. And you see, for any particular point, for example, if I take the point where y of 0 equals ln of 2, there's a unique one of these solutions passing through that point. And so we have a similar thing going on with solutions for differential equations. In general, we write the general solution to a differential equation in this form. It's usually y equals some function of x with some constants involved, which could take any particular value. So solution, the general solution to a differential equation, is in fact a family of solutions where you have some constants which can be varied to get different particular solutions. So an initial value problem asks for a specific solution to the differential equation, satisfying some initial condition that y of some particular value has to be equal to, again, y naught, some particular value of y. So an example of an initial value problem would be to use this general solution, which is something we'll solve for later. Suppose I know that this is the general solution to this differential equation. An initial value problem would say, find the particular solution to the differential equation y prime equals x minus y with the property that y of 0 equals 0. And so there's a unique solution in this family which satisfies that. You set x equal to 0, and you have y of 0 equals 0, so all of this should be 0, and then you can solve for c to figure out what's going on there. If I have a differential equation of this type, where y prime equals some function of x and y, and this is a function of two variables, so it's some combination of x's and y's, then I know that the slope of any one of these solutions at a particular point xy is given by this combination of x and y's on the right, because y prime here is the derivative of the solution. So think about this equation, y prime equals y minus x. Then I know that at the point in the plane x equals 2, y equals 1, the solution that passes through that point, I have a formula for its slope. It's y minus x, or 1 minus 2 at that particular point. And so the slope, or the tangent to the solution passing through that point, has slope minus 1. And at another point in the plane, for xy equal to 0, 1, again I can use the formula for the derivative, which is y minus x, or 1 minus 0, which is 1, to determine the slope of the solution that passes through that point. Remember, we said before that given any particular point on the plane, there is usually a unique solution passing through that point. And I say usually because there are exceptions to that rule. The graph of a solution to this particular differential equation from the family of solutions passing through the point xy equals minus 1, 1 also has slope y minus x, which is 2. So it's sloping upwards, and the tangent has slope 2. And we can get some idea of what the graphs of solutions look like by drawing something called a direction field, or even a slope field. And to do this, we take a number of points on the plane, and we calculate the slope of the solution passing through that point, as we did on the previous page. And then we draw a little arrow pointing in that direction from that point. And so here's a bunch of arrows drawn by the computer, and this shows the slope of the solutions to the differential equation y prime equals y minus x at all of these points. You can see here it shows a grid of points, and of course the more points you choose, the better the picture you get showing what's happening, the solutions at these particular points in the plane. And this thing is called a direction field, and it basically shows you where the solutions are headed at many points in the plane. The more points you have, the better the picture you have of what these solutions are doing. And you can use this to sketch a solution. So you can draw your direction field. And here we have the direction field for the equation y prime equals y minus x. And suppose you're asked to solve the initial value problem where y of 1 equals 3. So you're looking for that unique solution that passes through the point 1, 3. Well, you can figure out where this point is on the plane, and you can see what's happening, the arrows at that point. So the arrows tell us that the solution is headed in this direction, and so we can basically follow the arrows here and draw a rough sketch of the solution. And of course we can backtrack because the arrows are coming in from this direction, and we can draw the other half of the solution in the opposite direction. So this gives us a method for sketching a solution. We draw the direction field, we pick the initial point, and we figure out where the arrows are going, and that gives us a sketch of that solution which passes through that particular point. Suppose I were to take the point 2, 0, and I wanted to sketch the solution to this differential equation y prime equals y minus x, which passes through that point. Well, essentially I follow the arrows. I start at this point, I see the arrows are moving in this direction, so I draw a rough sketch of where the arrows are going, and then I can see the arrows are coming from this direction, so this gives me a rough sketch in the other direction. Here we have a rough sketch of many solutions, and this is one use of this direction field. Euler's method makes this idea of following the arrows a little more precise, and so this essentially uses the direction field to get an approximate solution to the differential equation. So given a differential equation, Euler's method approximates the path of a solution with a series of line segments which basically follow the direction of the arrows in the direction field. But more than that, it writes down the actual values of some points on this curve, so you can actually use this sketch of the solution to make some predictions about what will happen to the curve passing through that point. So Euler's method applies to differential equations y prime equals f of xy, where I have a formula for the derivative of y with respect to x in terms of x and y. And here's a typical example of what I might want to do with Euler's method. Suppose I have the differential equation y prime equals y minus x, and I start at the initial point with y of 2 equals 0, and I want to make a prediction about the value of y of 4. So if I start at this initial point where y of 2 equals 0, there's a unique curve passing through that point which satisfies this particular differential equation. So this differential equation tells me how that curve is changing, and I can get an estimate of what that curve looks like using Euler's method, and use that estimate to predict the value of y4. The first part of this is we choose the step size of our approximation, and this will be the change in the value of x for each line segment. And in general, a smaller step size means shorter line segments and a more accurate approximation. And so we're going to use a step size of 0.2 for this particular example. And here's basically how Euler's method works. So we start at the point where y of 2 equals 0. So with k equals 0, the number of steps at 0, we have our first point on the estimated curve is x0, y0, which is just the initial point. And from there, we follow the path of the arrow in the direction field, which starts at the point 2, 0. And that gives us the slope of the tangent to the actual solution. We've shown the actual solution here in green, and we follow that arrow until we get to the point where x1 equals x0 plus h, x0 plus our step size. So until the change in the x's is equal to our step size, which is 0.2. And this gives us a new point on the curve called x1, y1. And then from there, we follow the direction of the arrow in the direction field until the x's have changed by the step size, which is 0.2. And so that brings us to a new point, x2, y2. And then from there, we follow the arrow in the direction field from that point until the x's have changed by 0.2. And you can see here we're staying pretty close to the actual solution, but we're off by just a little bit. But of course, the whole point of estimation is that you don't know the actual solution, so you may be off, and in fact you're guaranteed to be off 90% of the time, but you don't know exactly where the actual solution is, so you're using your estimate to estimate what's going to happen in the future to this curve. From the point x3, y3, we follow the arrow in the direction field until the x's have changed by 0.2 to x4, y4, etc., etc., etc. So we keep doing this, and we have to do this for 10 steps before the x value becomes 4. And when it does, we get to, after 10 steps, we get a point x10, y10, and y10 is our estimate for the value of y when x is 4. You can see again it's off the true value a little bit, but that's the estimate. And so it's minus 13.5752. And so when we work through this, as we work through, we can actually write down a formula for x1 and y1, x2 and y2, etc., etc. Remember, we know the actual value of the initial point, x0, y0, and we have that because we're following a line segment here, the difference in the y values between y0 and y1 is the difference in the x's, which is h, the step size, times the slope of this arrow, which is given by f x naught y naught because we're following the arrow in the direction field that starts at x naught y naught. And so therefore we have y1 equals y naught plus h, the step size, times f of x naught y naught. We have x1 equals x naught plus the step size plus 0.2, and y1 is y naught plus 0.2 times minus 2, so it's minus 0.4. And since we're just repeating the process to get x2, y2, we have the same thing again. Starting at x1, y1, we follow the arrow, we get x2 equals x1 plus h, and y2 equals y1 plus h times f of x1, y1. And similarly, we get equations for x3, y3, and after 10 steps, we have an estimate for y of 4. So, in summary, we start at the initial point, we choose our step size before we start, and the smaller that step size is, the more accurate our prediction will be. And in order to get to our solution in an integral multiple of steps, we should look at the interval between where we are and where we want to be and make sure we're dividing that up into n steps for some natural number n. And we have some formulas for x1, y1 in terms of x0, y0, and x2, y2 in terms of x1, y1. So basically we can make a table, and we can fill in this table step by step, and this allows us to get our prediction for y4, which is y10 in this particular instance. That's y subscript 10, the value of y after 10 steps.